A fusion experiment is a fire hose of data. Thousands of sensor channels sampled tens of thousands of times a second across shot after shot after shot. Buried in that flood are the patterns that separate a good plasma from a disruption. Machine learning is how we pull those patterns out, and it is a toolbox, not a single trick. The workhorse is supervised learning. You take plasma states where you already know the answer. This one was stable, this one was heading for trouble. And you train a model to predict the label from the signals alone. Feed it enough well-labeled examples, and it generalizes to states it has never seen, which is precisely what we need when the next plasma is never quite like the last. Sometimes there are no labels at all, and that is where unsupervised learning earns its keep. Turned loose on raw signals, it finds the natural structure on its own, clustering operating regimes, surfacing the hidden groupings a human never thought to look for. Often, it is how we discover that a category we never named was there all along. Underneath most of this sit neural networks, layers of simple units, each applying a weight and an activation, stacked so that the whole can represent astonishingly complex relationships between input and output. Training is just the patient adjustment of those weights, example by example, until the output matches reality, and the surprising thing is how far that simple recipe scales. The architecture should fit the data. For two-dimensional plasma profiles and images, convolutional networks sweep small kernels across the field, detecting local shapes and textures wherever they appear. The right tool for spatial structure, and one that learns the same feature once and finds it everywhere. For signals that unfold in time, we reach for recurrent networks and LSTMs. They carry a memory cell forward through the sequence, so the model can weigh what just happened against what happened a moment ago. Essential for a plasma whose future depends on its recent past. More recently, transformers changed the game. Instead of marching strictly step by step, attention lets the model look across an entire sequence at once and decide which moments matter most for the question at hand. It is a powerful way to find long-range structure in messy signals. And when the data is a network rather than a grid, sensors wired across a machine or the nodes of a simulation mesh, graph neural networks pass messages along the connections themselves, learning directly on the structure of the problem. When the geometry of the machine is part of the answer, it belongs inside the model, not flattened out of it. Raw signals are rarely the best input. Physics-informed features, quantities we already know matter, engineered from first principles, give the model a head start. Feeding it good physics beats making it rediscover physics from scratch, and it means the model needs far less data to reach the same skill. Good features are how decades of plasma theory get handed to the network for free. With power comes a hazard: overfitting. A model can memorize the training set and fail utterly on anything new. We watch the training curve and the validation curve, and when they diverge, we know the model has started memorizing. Regularization is how we hold it back and keep it honest. Two ideas stretch a limited data set. Transfer learning takes a model trained in simulation and adapts it to real hardware, the sim-to-real bridge, so we don't start from zero at first plasma. And active learning lets the model choose its own next experiment, asking for the data that would teach it the most. We rarely bet on one model. Ensembles combine many models into a single estimate, and the spread between them is itself information, a natural measure of confidence. Autoencoders, meanwhile, compress a plasma state down to a compact latent code and reconstruct it, giving us a lever on both denoising and anomaly detection. When a signal cannot be rebuilt from that code, something genuinely unusual is happening. And every one of these methods in our hands reports its own uncertainty. Bayesian deep learning gives a network genuine error bars, so a prediction arrives with a statement of how much to trust it. These models advise, they never decide alone. The deterministic rules engine holds the final word inside hard physics limits. Used this way, machine learning becomes a powerful advisor without ever becoming an unaccountable one. That is the discipline that lets us use machine learning